All right, let's jump right in. Today, we're going to demystify something called charge density. And trust me, we're going to start with a really simple idea and end up with a mind-bending quantum truth that might just change the way you think about, well, everything.
So, have you ever really thought about it? That little battery in your phone, a massive storm cloud, even a simple copper wire, they all hold an electric charge. But how concentrated is it? How much of that electricity is crammed into any given space? That's the big question we're tackling today. And the concept that gives us the answer is, you guessed it, charge density. It's the one physical quantity that tells us exactly how packed in that electricity really is. At its core, it's actually a pretty simple ratio. It's just the amount of charge divided by the amount of space it's in. The best way to think about it is like mass density. You know how a block of styrofoam and a block of lead can be the exact same size, but one is way, way heavier? That's because the lead has more mass packed into the same volume. Well, charge density is the exact same idea, just with electric charge instead of mass. Simple, right? Okay, but that word space can mean a few different things. It could be a one-dimensional line, a two-dimensional area, or a three-dimensional volume. And depending on the shape of the object we're looking at, this gives us three different, let's call them flavors of charge density. So for a 1D object, like a long, thin wire, we talk about linear charge density. We use the Greek letter lambda for that. Then for a 2D object, say the surface of a metal sheet, we use surface charge density, or sigma. And finally, for a full 3D object, like a charged ball, we've got volume charge density, which we call rho. See? It's a nice, neat, tidy way of looking at the world, all courtesy of classical physics.
But, and you knew there was a but coming, here's where our story takes its first big twist. This beautifully simple picture of charge being spread out all smooth and even, well, it's not quite the truth. It's actually more of a very, very useful illusion.
Yeah, in the classical view, we treat charge like it's some kind of continuous fluid. We imagine we can just keep dividing it up forever, that it's smeared perfectly evenly across an object, just like spreading butter on toast. And look, it's a great approximation. It makes the math work out really nicely. But is that really what's going on at the microscopic level? As you've probably guessed by now, the answer is a big no. When we start to zoom in, that smooth, buttery picture completely falls apart. So here's the reality check. All real charge is carried by actual individual particles. We're talking electrons, ions, you name it. It's way less like butter on toast and a lot more like sprinkles on a cupcake. You've got these tiny, distinct points of charge with, empty space in between them. So why on earth does our continuous illusion work so well? It's all about the sheer, staggering number of those sprinkles. This number on the screen? That's roughly how many free-moving electrons you'd find in a single cubic centimeter of copper. With that many particles all crammed together, from our human-sized perspective, it looks perfectly smooth. The approximation isn't just good, it's incredibly accurate. And just when you think you've got it figured out, things get really weird and really cool. It turns out, if we zoom in even further, past the individual sprinkles themselves, reality kind of loops back around in this bizarre way. Welcome to the quantum level. You see, according to quantum mechanics, a tiny particle like an electron doesn't actually have a single fixed position in space. Not until we measure it, anyway. Instead, it exists as something called a wave function, which is basically just a cloud of probabilities. It's a map of all the places the electron could be at any given moment. And here is the final amazing twist. Because the electron's location is a probability cloud, its charge is also a probability cloud. At this fundamental quantum level, the charge of a single particle isn't a point at all. It's literally smeared out in space, creating what chemists call an orbital. So in the strangest way, the idea of a continuous charge distribution becomes real again, but this time for a single tiny particle. How wild is that? Okay, let's take a breath. We've gone from a simple model to discrete particles and now to this bizarre quantum cloud. But you're probably thinking, so what? Why does any of this matter in the real world? Well, let's zoom back out and see why this is so important. See, understanding charge density at this quantum level is not just some academic exercise. It's absolutely fundamental. The way those electron probability clouds, those orbitals, overlap and interact with each other, that is literally what creates chemical bonds. It's the basis of all of chemistry. And by understanding that, engineers can do incredible things, like designing new molecules from scratch or creating advanced water filters that are so precise they can pull out specific ions just based on the shape and density of their charge clouds. So we'll leave you with this to think about. We started this journey with the idea of charge being packed into an object, and we ended by realizing that the charge of a single fundamental particle is itself spread out in a cloud of pure possibility. So if the very building blocks of our world aren't solid little points, but are actually these fuzzy clouds, what does that really say about our whole idea of solid matter? It's a fascinating question to chew on. Thanks for joining us.